The chair beneath you is there right now, even though you are not looking at it. You believe that without a second thought. The moon hangs in the sky whether or not anyone watches it. The coin in your pocket is already heads or tails as it sits in the dark, and measuring something only reveals what was already true. This is the most reasonable belief a person can hold. And in October of 2022, 3 physicists were handed the Nobel Prize for proving it false for the smallest pieces of the world. They did not argue it. They measured it in laboratories from Berkeley to Vienna, using entangled particles, polarizing filters, and even the ancient light of quasars billions of years old. Every time, the universe gave the same answer. The particles you are built from do not carry settled properties waiting to be found. So if the tiny things that make up everything are not real in the way you assumed, what is holding the solid world together while no one is looking? Get comfortable. Hit subscribe if you're new here, because by the end of this, the word real will not mean quite what it did when you sat down. Now, let's slowly ease into this. Part 1. A prize for proving reality isn't real. On the 4th of October, 2022, a small committee in Stockholm did something that committees almost never do. They handed the most respected prize in all of science to 3 people for proving that reality is not what you think it is. The prize was the Nobel Prize in Physics, and it went jointly to Alain Aspect, John Clauser, and Anton Zeilinger. The words the committee chose are worth hearing exactly, because they are unusually blunt for an institution that usually hides behind careful language. The 3 men were honoured, the citation said, for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Read that again slowly. Not exploring, not investigating, establishing. The committee was telling the world that a question had been settled, and that the answer overturned something almost everyone quietly believes. The thing that got overturned has a name. Physicists call it local realism, and for tonight you can think of it as the last comfortable idea about the universe. It is the picture of the world you carry without ever having chosen it, the one your mind hands you for free the moment you open your eyes in the morning. And across half a century of patient, careful, almost unbearably clever experiments, 3 people showed that the universe does not actually run on it. I want to sit with that phrase, local realism, because everything tonight depends on it, and it is made of 2 separate ideas that feel so obvious they are almost invisible. The first idea is locality. Locality says that things are only affected by their immediate surroundings. You cannot reach into a galaxy hundreds of light years away, flick a switch, and change something here in this room in the same instant. Nothing, not even a whisper of information, travels faster than light. That is not a rule someone invented to be tidy. It is woven into the structure of space and time themselves, and it is the one contribution of Einstein's that survives this entire story completely intact. The second idea is realism, and realism is much harder to pin down, which is exactly why it took the smartest people alive 30 years to figure out how to test it. Realism is the belief that things have definite properties, whether or not anybody is looking at them. The particle is already spinning one particular way before you measure it. The coin has already landed heads or tails before you lift your hand to check. The old question about a tree falling in an empty forest is really a question about realism, and the realist answers it without hesitation. Of course, the tree makes a sound. The sound is a fact about the world, and the world does not wait for a listener before it decides what is true. Put those 2 ideas together, and you get the universe almost everyone assumes they live in. It is a universe made of real things that carry their own properties around with them, and those things can only nudge their neighbours, never anything far away, and never faster than light. It is a calm, sensible, local, real universe. It is also, as it turns out, not the one we actually inhabit. Here is the strange gift at the center of this story, the thing that makes it more than a physics lecture. This is not a tale of a genius being proven right. We have plenty of those. This is the rarer and stranger tale of some of the most brilliant minds who ever lived being confused for decades, and of Albert Einstein, of all people, being wrong about the deepest thing he ever argued for. Einstein was not usually wrong. That is part of what makes this land the way it does. The man who rewrote our understanding of space, time, gravity, and light looked at the quantum world, said this cannot be the whole truth, built the single sharpest objection anyone has ever raised against it, and lost. He did not lose because he was careless. He lost because the universe turned out to be stranger than even he was willing to imagine, and he was a man who had already imagined some very strange things. That is the vertigo I want you to feel tonight, not fear, just the slow tilt of the floor as an assumption you did not know you were standing on gets quietly pulled out from under you. You should also know, before we go any further, what this is not. It is not a story about faster-than-light phones or telepathy or messages sent across the galaxy in an instant. The universe closed that door too, and closed it firmly, and by the end of tonight you will understand why the correlations we are about to explore are real and measured and impossible to explain away, and yet still cannot carry a single word of a message. The universe found a way to be spooky and lawful at the same time, and threading that needle is one of the most elegant things it does. So this is where we are going over the next couple of hours, slowly, with no rush and nothing to startle you. We are going to walk the whole road that led to that morning in Stockholm. We will start in the 1930s, when the argument was young and nobody could see how it would ever end. We will meet Einstein at his sharpest, building an objection so good it froze the field for a generation. We will meet an Irish physicist on his summer break, who found a crack of light in a wall everyone else thought was solid stone. We will follow the experiments, one after another, each one sealing off another escape route, until there was nowhere left for the comfortable universe to hide. And along the way, every so often, I will ask you to hold a small picture in your mind, because this subject lives or dies on pictures. Right now, hold just one. Hold the image of that committee in Stockholm, on an ordinary autumn morning, reading out a sentence that says, in effect, the world is not locally real. Nobody rioted. The sun came up as usual. Most people never heard about it. And yet what those three physicists established is arguably the most unsettling verified fact about existence that our species has ever pinned down, sitting quietly in a press release, while the rest of the world worried about other things. The question that should be forming in your mind right now is a simple one, and it is the question this entire video exists to answer. How could you possibly prove such a thing? How do you take an idea as slippery as whether a particle is real before you look at it, an idea that sounds like pure philosophy, like the kind of thing you argue about at 2 a.m. and never resolve, and turn it into a number you can measure in a laboratory? That is the miracle at the center of this story, and it has a name and a date and a person attached to it. But to understand how anyone cracked it, we first have to go back and look very carefully and very gently at those two quiet assumptions again, because the whole trick was in noticing that they could be pulled apart. Part 2. The two assumptions you didn't know you had. Let us take these two assumptions apart slowly, one at a time, because the entire proof depends on the fact that they can be separated at all. Start with locality, since it is the friendlier of the two. Locality is the idea that the world is stitched together locally, that causes touch their effects, that influence spreads the way ripples spread across a pond, moving outward from where the stone fell and never simply appearing on the far shore. When you clap your hands, the sound reaches the far wall a moment later, not instantly, because the pressure wave has to travel through the air to get there. When the sun brightens, the extra warmth reaches your face 8 minutes later, because that is how long light takes to cross the gap between here and there. Nothing you have ever experienced has broken this rule. Every effect you have ever seen had a cause that reached it in time, moving at some finite speed, arriving from somewhere nearby. Einstein took this everyday intuition and made it into something far more rigid and far more beautiful. In his relativity, the speed of light is not merely the speed of a particular thing that happens to be fast. It is the speed limit of cause and effect itself. It is the fastest that any influence, any signal, any scrap of information can possibly travel, and it is the same for everyone, everywhere, no matter how they are moving. This gives us a clean way to say when two things are truly cut off from each other. If two events happen far enough apart in space and close enough together in time that not even a beam of light could make the journey between them, then neither one can have caused the other. They are sealed away from each other. Physicists call this being space-like separated, and the phrase is worth holding on to because it is the exact condition the experiments will work so hard to create. I want to give you a moment to feel the shape of this before we move on, because it is one of the quietly beautiful facts about the universe, and it deserves a slow breath. Picture the emptiness between the stars. Picture a single pulse of light setting out from one of them, crossing that darkness at the one speed the universe truly honors, taking years, taking centuries to reach the next. Everywhere, in every direction, causes are traveling outward like this, never leaping, never skipping ahead, always paying the toll of distance in the currency of time. The universe has a pace. It has a grain to it, a texture, a fixed rhythm at which here is allowed to touch there. Locality is just the name for that rhythm, the promise that nothing gets to cheat it. Hold that stillness for a second. It is the promise we are about to watch the universe appear to break, and then, in the strangest twist of all, keep after all. Now come to realism, which is the assumption that does the real work tonight, and which is so ingrained in us that most people cannot even hear it as an assumption. Realism says that the properties of things are already settled before anyone measures them. The world is full of definite facts, and measuring is nothing more than looking those facts up, the way you might open a drawer to find the spoon that was already lying there, whether or not you opened it. Think about how total your faith in this is. You believe, without a flicker of doubt, that the moon is somewhere specific right now, even though you are not looking at it. You believe the coin in your pocket is either heads up or tails up as it sits there in the dark, and that checking would only reveal a fact that was already true. You believe the tree in the empty forest, when it falls, sends out real waves of pressure through real air, and that calling those waves a sound or not is just a quibble about words, because the physical event happened regardless of any ear. This is realism. It is the belief that reality is fully written down at all times, and that observation is a kind of reading, never a kind of writing. Here is the hinge of the whole story, the thing you have to let yourself take seriously, even though everything in you resists it. What if that is not true for the very small? What if, down at the level of a single particle, a single photon, a single electron, the property genuinely is not there until it is measured, not hidden, not merely unknown to us because we are not clever enough or our instruments are too clumsy. Actually, truly, not yet decided. The particle exists in a blur of possibilities, a kind of smeared out, maybe, and only when it is forced to interact with a measuring device does it commit to a single answer, the way a spinning coin is neither heads nor tails while it is still in the air. That is not a claim about our ignorance. That is a claim about the world. It says the drawer is empty until you open it, and the act of opening is what puts the spoon inside. It says the coin decides what it is at the very moment you catch it, and not 1 instant before. Everything in your daily experience screams that this is absurd, and for objects your size it is absurd, which is exactly why It took the finest minds of the 20th century so long to work out whether it might nonetheless be true for the things you are made of. Notice, and this is the crucial move, that these two assumptions are separate. Locality is about how far and how fast influence can travel. Realism is about whether properties exist before measurement. You could imagine a universe that is local but not real, where nothing travels faster than light, but particles have no definite properties until observed. You could imagine a universe that is real but not local, where everything has definite properties, but they can somehow be linked across any distance instantly. And you could imagine, as almost everyone did for centuries, a universe that is both comfortable and sensible on both counts at once. For a long time, it seemed impossible to ever separate these two ideas experimentally, to design a test that could tell you which one, if either, the universe was quietly violating. They seemed too tangled together, too philosophical, too far from anything you could put on a laboratory bench and measure with a dial. And that impossibility, that sense that this was a question forever beyond the reach of experiment, is precisely the wall that this story is going to break through. But to understand how the wall came down, you have to understand how it was built and who was standing on either side of it. Because before anyone found a way to ask the universe this question directly, there were two great camps of physicists who disagreed about the answer, and they disagreed with all the force and stubbornness and brilliance that only people who are absolutely certain and cannot prove it can bring. One of those camps was led by the most famous scientist in the world, and the astonishing thing, the thing history did not see coming, is that he was about to be wrong. Part 3. Two camps in the 1930s. By the early 1930s, physics had split into two ways of thinking about the smallest things in existence, and the split ran right down the middle of the field between people who otherwise admired each other enormously. On one side stood Einstein and those who thought like him, and their position was the one you already hold in your bones. They believed the universe is real. A particle, an atom, an electron, a photon, all of these have definite properties that belong to them, that are simply theirs, present and settled, whether or not any measurement is ever made. If an electron is spinning, it is spinning a particular way right now, and the job of the physicist is to find clever enough instruments to reveal what was already the case. Measurement uncovers. It does not invent. To this camp, the idea that a property might not exist until observed was not profound or mysterious. It was a confession that the theory was unfinished, a placeholder where a real explanation ought to go. On the other side stood Niels Bohr and the group around him, working mostly out of Copenhagen, and their view was one of the strangest ideas ever to become mainstream science. They argued that particles do not have properties that have made up their minds until you actually go out and measure them. Before measurement, a particle does not sit at a single value waiting to be found. It exists across a whole spread of possibilities at once, described by a mathematical object called the wave function, which does not say the particle is here or there, but assigns a kind of weight to here and to there and to everywhere in between. Only when a measurement happens does the particle settle all at once onto a single definite answer. The anti-realists were not saying we are ignorant of the particle's true state. They were saying there is no single true state to be ignorant of, not until the world forces the question. You can feel how offensive this was to the other camp and to something in yourself. It sounds like a word game or a cop-out or mysticism dressed in equations, and yet it was not fringe. It became, over the following decades, the standard working view of most physicists on Earth, taught in every classroom, used every day, because whatever it meant, it worked. The equations built on it predicted the results of experiments with a precision unmatched by anything in the history of science. That is the maddening thing that sits under this whole argument. The strange side kept being useful, and useful in physics has a way of quietly becoming true. To show just how absurd he found this idea, one of the physicists on the skeptical side, Erwin Schrödinger, cooked up a thought experiment so vivid that it escaped the seminar room and became one of the most famous images in all of science. He asked you to imagine a cat sealed inside a box. Inside the box with the cat is a single radioactive atom, and that atom obeys the strange quantum rules. Over the next hour, the atom might decay, or it might not, and quantum mechanics insists that until it is measured, it is genuinely in a blur of both, decayed and not decayed at once. Schrödinger then rigged the box so that if the atom decays, it triggers a mechanism that kills the cat, and if it does not, the cat lives. Now play the quantum rules forward honestly. If the atom is truly in a blur of decayed and not decayed, then the trigger is in a blur of fired and not fired, and the cat, following the chain link by link, is in a blur of dead and alive. Not hidden behind the box's walls, one or the other, waiting for you to find out. Actually both, smeared together until the moment someone opens the box and looks, and only then does reality snap to a single answer, and the cat become, at last, definitely one thing. Schrödinger meant this as a knockout blow. He was saying, look at the ridiculous place your logic leads. A cat cannot be both alive and dead. This is a reductio, a way of proving an idea false by following it to an obviously insane conclusion. But history played a joke on him. The thought experiment was so vivid that it outlived the objection it was built to make. Today, most people who have heard of Schrödinger's cat think of it as the emblem of quantum weirdness, the very thing Schrödinger was mocking, rather than as his attempt to laugh the weirdness out of the room. The universe, it seems, has a sense of humour, and it enjoys turning skeptics into mascots for the thing they doubted. I want to give you the single sentence that captures the anti-realist position, because it is going to come back tonight, and each time it returns, it is going to weigh a little more. The sentence is this: none of it is real until you look. Say it quietly to yourself. It sounds, right now, like a poem or a provocation or a piece of undergraduate philosophy you can safely ignore. Hold on to it anyway. By the end of this video, that sentence will have stopped being a slogan and started being something closer to a laboratory result. And I want you to remember that there was a moment early on when it still sounded like nonsense. So that was the standoff. On one side, Einstein and realism, the world is definite whether or not you look. On the other, Bohr and the anti-realists, the world is a fog of possibility that only condenses into fact when measured. And here is what made the argument so agonizing, so perfectly stuck, so maddening to everyone involved. Both sides predicted exactly the same results for every experiment anyone could actually perform. Every measurement came out the same, whether you believed the property had been there all along or believed it sprang into being at the moment of looking. The two philosophies wore identical clothes. There was no dial you could read, no needle that would swing one way for realism and the other way for its denial. The disagreement seemed to live entirely in the interpretation, in the story you told about the numbers, and not in the numbers themselves. This was not a polite disagreement conducted at a distance. Einstein and Bohr argued in person, repeatedly, most famously at a series of grand meetings called the Solvay Conferences, where the greatest physicists of the age gathered in a single room. The stories from those meetings have become legend. Einstein would arrive at breakfast with a new thought experiment designed to trap quantum mechanics in a contradiction, some ingenious imaginary device that seemed to measure the unmeasurable. Bohr would spend the day turning it over, and by dinner he would have found the flaw, the overlooked effect that rescued the theory. The next morning, Einstein would come back with another. They pushed each other for years, two giants who respected each other enormously and disagreed about the nature of reality itself. Neither ever truly convinced the other. Einstein went to his grave, believing quantum mechanics was incomplete, and Bohr went to his believing. Einstein had simply refused the lesson the universe was teaching. What neither of them had, what neither of them could have, was a way to settle it by measurement. That is the gift the next generation would inherit. For a while, the greatest minds in physics simply agreed to disagree, or worse, agreed to stop asking, because asking led nowhere. You picked your side based on temperament, on taste, on what kind of universe you could stand to live in, and then you got on with the calculations. Einstein could not stand a universe without definite properties, so he was a realist. Bohr had made his peace with the fog, so he was not. And no experiment on Earth could tell them who was right, except that Einstein was not finished. He was never one to leave an argument as a matter of taste if he could turn it into a matter of logic. And in 1935, together with two younger colleagues, he was going to write down an objection so precise, so carefully built, that it would corner quantum mechanics in a way nothing had before. He thought he had found the flaw that would bring the whole strange edifice down. He was about to make the sharpest argument of his life. What he did not know, what he could not have known, was that the very sharpness of that argument was the thing that would eventually be used to prove him wrong. Part 4. Einstein's perfect objection. In 1935, Einstein, together with two colleagues named Boris Podolsky and Nathan Rosen, published a short paper in the journal Physical Review, and its title was a question: can the quantum mechanical description of physical reality be considered complete? Their answer, argued with great care, was no. Physicists have called it the EPR paper ever since, after the initials of the three authors, and it is one of the most productive wrong ideas in the history of thought. The argument rests on a phenomenon that had just been given a name. That same year, Schrödinger, replying to the paper, coined the German word Verschränkung, which we translate as entanglement, and he said something remarkable about it. He said entanglement was not merely one interesting feature of quantum mechanics among many. It was, he wrote, the characteristic trait, the one that forces the entire departure from classical thinking. Entanglement is the idea that two particles can be linked so that their properties are bound together, described by a single shared wave function, no matter how far apart they drift. Einstein and his colleagues built their objection on top of two conservation laws so solid that no physicist would dream of doubting them. The first is conservation of momentum. Things do not simply start moving in a direction unless something pushes or pulls them. The second is conservation of angular momentum, which is the spinning version of the same idea. Things do not start rotating unless something twists them. These are among the most reliable rules we have, tested countless times, never once seen to fail. Now follow the thought experiment, because it is elegant and you can hold all of it in your head at once. Take a single quantum particle that is sitting still and not spinning, with zero total momentum and zero total spin. Let that particle break apart into two smaller pieces that fly off in opposite directions. Conservation forces a strict bookkeeping on those two pieces. If one flies to the right, the other must fly to the left, so the momentum still adds up to zero. If one is found spinning clockwise, the other must be spinning counterclockwise, so the spin still cancels. The two pieces are entangled. Whatever you find for one, the other must be its perfect opposite in order for the books to balance. I want you to slow down and actually be there for this, because it is the moment the whole argument turns. Picture yourself shrunk down to the scale of that single particle, floating beside it in the dark, in the instant before it splits. It is perfectly still. There is nothing to see, no motion, no spin, just a quiet knot of possibility hanging in front of you. Then, silently, it divides. Two pieces drift apart. one drifting past your left shoulder, one past your right, moving away from each other at a steady pace. You follow neither. You just watch them go, out of the room, out past the walls, out past the sky, one heading toward the moon and beyond, one heading the opposite way into the far dark. Minutes pass, years could pass. The two pieces are now light years apart, farther than any signal could quickly cross, and here is the thing to hold in your mind as they separate. Nobody has measured either one. Neither piece, according to Bohr, has yet decided which way it is spinning, and yet you know, with total certainty, that the instant anyone measures one, it will turn out to be the exact opposite of the other. Are the answers already written into them, packed like a secret, at the moment they split? Or are two particles, now separated by an impossible gulf, somehow going to settle the question together in the same instant across all that emptiness? Sit in that suspense. It is the exact suspense Einstein sat in. Here is how Einstein resolved it, and his reasoning is so reasonable that you will want to agree with him, and you should let yourself for now. Suppose you measure the near particle and find it spinning clockwise. Instantly, you know the far particle is counterclockwise, but the far particle might be light years away. If it truly had no definite spin until this moment, then your measurement here would have had to reach across all that distance and force the far particle to choose, faster than light, in violation of locality, which Einstein held sacred. He found that intolerable. Influence cannot travel that fast. It cannot travel infinitely fast. Therefore, he concluded, the far particle must have had its spin decided all along, from the very moment of the split, and so must the near one. The answers were written into both of them at birth. We simply did not know the values, because quantum mechanics does not tell us. There must be some deeper layer of the theory, some information the equations leave out. Einstein gave that missing information a name. He called it hidden variables. The particles carry hidden variables, settled at the start, that determine what every measurement will find. Quantum mechanics, by failing to describe them, is not wrong, he said. It is incomplete. It is a true theory with a hole in it, a map that leaves off some of the roads. Fill in the hidden variables and the spookiness vanishes, replaced by the ordinary, local, real world we all expect. Let me give you the picture that makes his position feel as sensible as it truly is, because he deserves that much. Imagine you own a single pair of gloves, one left and one right. You pack each into its own box without looking, ship one box to Tokyo and the other to Lima, thousands of miles apart. Now a friend in Tokyo opens her box and finds the left glove. In that instant, she knows, with perfect certainty, that the box in Lima holds the right glove. Did anything travel between the cities? Did opening the Tokyo box reach across the ocean and force the Lima glove to become right-handed? Of course not. The gloves were left and right from the moment you packed them. The correlation is real, it is perfect, and it is completely boring. Nothing spooky happened at all. That, said Einstein, is all entanglement really is. Left glove in Lima, right glove in Tokyo, decided at the start, merely revealed at the end. Hold that image, the two gloves in their two boxes on opposite sides of the world, because it is the most persuasive thing in this entire story, and it is going to come back much later wearing a very different face. For now, let it do its work. It makes Einstein's view feel not just defensible, but obviously correct. Particles carry their properties the way a traveller carries a packed suitcase. The suitcase was packed before the journey. Opening it at the destination reveals what was inside all along. Notice how modest Einstein's demand really was. He was not asking for magic or for some exotic new force. He was asking only that the world make ordinary sense, that particles carry their properties the way everything in your daily life carries its properties, settled and portable and local. He was defending common sense itself, armored with rigorous logic. That is what makes this the most sympathetic wrong idea in the history of physics. When you side with Einstein here, you are siding with every instinct evolution ever gave you about how objects behave. He was not being stubborn or foolish. He was being reasonable in the fullest and most human sense of the word. And the universe, as we are about to see, simply does not care how reasonable a thing sounds. This was Einstein at the height of his powers, and his objection was so good, so clean, so hard to answer, that it did something almost no argument in physics has ever done. It stopped the conversation for 30 years. Bohr wrote a reply, dense and difficult, insisting that the EPR authors had misunderstood what reality even means at the quantum level, but almost nobody could say cleanly who had won. Both sides still predicted the same experimental results. The gloves picture and the fog picture still wore the same clothes. And so the field did what fields do with a question it cannot answer. It set it aside, quietly, as a matter of philosophy, and moved on to problems that could actually be solved. For 3 decades, that was where it sat, a perfect, frozen standoff, with the most famous physicist in the world on one side and the establishment of quantum mechanics on the other, and no conceivable way to tell who was right. It would take a quiet, careful, largely unknown physicist working alone on his summer holiday to notice the one thing that everyone else, including Einstein, including Bohr, had missed. Part 5. 30 Frozen Years, and then Bell. The man who broke the stalemate was named John Stuart Bell, and in 1964 he was not trying to become famous. He was an Irish physicist, born in Belfast, who made his living designing particle accelerators at CERN, the great laboratory near Geneva. Quantum foundations were not his job. They were his hobby, the thing he thought about on the side, the puzzle he could not quite leave alone. And in 1964 he took a sabbatical, a stretch of leave from his ordinary work. And in that quieter time he turned his full attention to the old frozen argument between Einstein and Bohr. What Bell did is one of the most important intellectual moves of the 20th century, and I want to build up to it carefully because it is the moment metaphysics turned into physics. For 30 years, everyone had assumed the Einstein-Bohr question was unanswerable by experiment, because the two views always predicted the same laboratory results. Bell found the hidden crack in that assumption. He realized that everyone had been checking the two entangled particles at the same setting, measuring both for the same property, and asking whether they agreed. Of course, they always agreed. And of course, both theories predicted that agreement. The gloves match. The fog condenses into matching answers. At a single shared setting, the two pictures are truly identical. But Bell asked a different question. What happens, he wondered, if you do not measure the two particles the same way? What if Alice, holding one particle, measures it along one direction, while Bob, holding the other, measures his along a slightly different direction? And what if you do this over and over, changing the angles between the two measurements, and you keep careful track of how often the two results agree as you vary that angle? This is the stroke of genius, so let me make sure it lands. At matching angles, the particles are perfectly correlated. At completely opposite angles, they are perfectly anti-correlated. Everyone agreed on those two endpoints. The whole question is what happens in between, at the odd, mismatched, in-between angles, and how the rate of agreement climbs or falls as you sweep from one endpoint to the other. Bell proved something astonishing about that in-between region. He proved that if Einstein was right, if the particles carried hidden variables that fixed their answers in advance, and if no influence travelled faster than light, then the rate of agreement across all those angles could not exceed a certain ceiling. There was a hard limit, a mathematical wall, that any local, real, hidden variable universe simply could not climb over. no matter how cleverly you imagined the hidden variables were arranged. And then he showed the other half, which is the half that makes your skin prickle. Quantum mechanics, doing its own calculation for those same in-between angles, predicted a rate of agreement that rose above the ceiling. The fog was more coordinated than the gloves could ever be. At certain mismatched angles, entangled particles agree with each other more often than any locally real theory permits. The two pictures, which had worn identical clothes for 30 years, finally, at those strange in-between angles, predicted different numbers. It is worth dwelling on how strange and clever this move really was, because for 30 years everyone had been asking a question that could not decide anything. They had been checking whether the two particles agreed when measured the same way, and finding, unsurprisingly, that they always did. Bell's leap was to see that agreement at match settings tells you almost nothing, because both worldviews predict it. The information is hiding in the mismatches. By deliberately measuring the two particles at deliberately different angles, and by comparing the pattern of agreement across a whole family of those mismatched angles, Bell found the one place where a locally real universe and a quantum one keep different books. He did not need to see inside the particles. He did not need to know what the hidden variables were, or even whether they existed. He only needed to show that no possible set of them, however cunningly arranged, could reproduce the pattern quantum mechanics predicted across those angles. It was a proof about all conceivable local hidden variable theories at once, known and unknown, present and future. That is what gives it such tremendous power. Do you see what Bell had done? He had taken the most philosophical question in all of physics, the question of whether the world is locally real, the kind of question that sounds like it belongs in a late-night conversation and nowhere else, and he had turned it into a number, a measurable number, a quantity you could go into a laboratory with real equipment and real particles and actually determine if the number came in under the ceiling, Einstein was right and the world was locally real, its properties written in advance. If the number came in over the ceiling, then no local, real theory could ever explain it, and the comfortable universe was finished. This result is now called Bell's theorem, and the ceiling it describes is called a Bell inequality. There are many versions of it, expressed in different ways, but they all carry the same underlying idea. They all draw a line, and they all say that a locally real universe must stay on one side of that line, while quantum mechanics happily crosses to the other. For the first time in the entire history of the argument, there was a way to make the universe itself answer the question. There was a way to force it to show its hand. I gave you a phrase to hold earlier, and here is another one, maybe the most important of the night. After Bell, for the first time, the universe would have to pick a side. It could no longer hide in the ambiguity, in the shared clothing of two indistinguishable predictions. Someone could now build a machine, measure entangled particles at carefully chosen mismatched angles, add up the results, and read off which side of Bell's line the cosmos actually sat on. The universe would have to pick a side. Remember that sentence. We are going to watch it choose. Again and again. And we are going to watch it choose the same way every single time. There is something quietly moving about the fact that this breakthrough came from a man on his summer holiday working on a problem that was not his job, that most of his colleagues considered a philosophical dead end unworthy of a serious physicist's time. Bell himself, and this is important to who he was, expected the universe to come down on Einstein's side. He had a sympathy for the realist view. He found the fog distasteful, and part of what drove him was the hope that his theorem might eventually be used to expose quantum mechanics as the incomplete theory Einstein always said it was, and to reveal the deeper, saner, local reality underneath. He built the test hoping it would vindicate Einstein. Keep that in your mind too, because it is going to matter enormously how this story ends, and for whom. But in 1964, Bell's theorem was still only a piece of paper. It was a beautiful argument, a proof that the question could in principle be settled, but nobody had settled it. The trouble with a theorem is that it lives in the world of perfect idealized objects, of flawless detectors, and pure entangled particles, and measurements with no errors. Real laboratories do not have any of those things. Real detectors are leaky and imperfect. Real particle sources are messy. To go from Bell's clean mathematical wall to an actual number measured on an actual bench was going to take more than theory. It was going to take someone willing to build the machine. For a few years, that was the problem. Physicists had, at last, a question the universe could answer, and no apparatus capable of asking it out loud. Bell's theorem sat in the literature, admired by the few who noticed it, waiting. What it needed was an experimentalist, stubborn enough and skilled enough to turn the idea into hardware. And when that person arrived, he would come to the task, like Bell, quietly hoping to prove Einstein right. He would build the first machine ever capable of catching the universe in the act of choosing, and the universe was about to prove him wrong in the most personal way possible. Part 6. The sunglasses that shouldn't let light through. Before we can watch anyone build that machine, you need to understand the one piece of physics the machine actually uses. And the good news is that you can hold it in your own hands. It lives in a pair of sunglasses. The particles of choice for these experiments are particles of light, called photons, and a photon carries a property called polarization. Polarization is just the direction in which the light wave is wobbling as it travels. It might be wobbling up and down, which we call vertical, or side to side, which we call horizontal, or at any angle in between. To measure a photon's polarization, you send it through a filter called a polarizer, which is built to let through light wobbling in one direction and to block light wobbling in the perpendicular direction. Behind the polarizer, you put a detector, and now, when a photon arrives, you learn something. If it comes through, it was aligned with your filter. If it does not, it was not. This is not exotic laboratory equipment. The lenses of polarizing sunglasses are exactly this kind of filter, which is why they cut glare. Glare is mostly horizontally polarized light, bouncing off roads and water, and the sunglasses are built to block the horizontal and pass the vertical, so the harsh reflected light is filtered away while the rest of the world comes through. You have been carrying a piece of quantum measurement apparatus on your face at the beach without knowing it. Now I want you to actually do something, at least in your mind, because this is a demonstration you can perform with two lenses popped out of two pairs of polarizing sunglasses, and it will show you the strangeness with your own eyes. Sit at a table with a lamp or a window in front of you and hold up one polarizing lens. The world through it looks a little dimmer, a little tamed, but perfectly normal. Now take a second lens and hold it in front of the first, and slowly rotate it. As you turn it, the view through the pair grows darker and darker, and at one particular angle, when the two filters are crossed at 90 degrees to each other, the world goes black. No light gets through at all. It makes complete sense. The first filter only lets vertical light pass, and the second, turned to horizontal, blocks every bit of that vertical light. Two filters, crossed and darkness. Nothing surprising yet. Here is where the universe leans in and whispers something impossible. Keep those two crossed filters exactly where they are, dark as night, and now slide a third filter in between them, tilted to a middle angle, say 45 degrees. Your whole life has taught you that adding another filter can only remove more light. A third obstacle in the path should make the dark darker. Instead, light appears, the blackness lifts. Where a moment ago no light at all could pass, now some light slips all the way through the stack of three. You have added a barrier and gotten more light, not less. Sit with that for a moment, because it is genuinely, physically true, and it makes no sense at all if you think measurement merely reveals what was already there. So why does it happen? It happens because measuring a photon does not just read its polarization, it resets it. When light passes through that middle filter, tilted at 45 degrees, every photon that makes it through is no longer vertical or horizontal. It has been forced into a new definite state, a 45-degree state, by the act of passing through. The measurement did not find the photon's angle. It changed the photon's angle. And a photon now genuinely wobbling at 45 degrees has a real chance of getting through the final horizontal filter, because 45 degrees is halfway between vertical and horizontal, and halfway means it can go either way. Remove the middle filter, and the light hitting the last filter is still purely vertical, and stays blocked, and the dark returns. Insert the middle filter, and it rewrites each photon on the way through, and the light comes back to life. This is the thing to carry out of this part, and into everything that follows. In the quantum world, measurement is not a passive act of looking. It is an intervention. It reaches into the particle and changes what is true about it. For a coin, checking which way it landed does nothing to the coin. For a photon, checking its polarization remakes the photon. That difference, invisible in the world of your size, is the whole reason the small world can do things the large world cannot. There is a simple rule hiding in the sunglasses, and it is worth naming because it reappears in the real experiments. The chance that a photon passes a filter depends on the angle between the photon's polarization and the filter, and it changes smoothly. Line them up perfectly, and the photon almost always passes. Cross them at 90 degrees, and it almost never does. Set them at 45 degrees, exactly halfway, and it becomes a coin flip, an even chance either way. That halfway point, the 50-50 angle, is where the quantum indecision is most naked, and it is no accident that the cleverest Bell tests place their filters near such in-between angles, where the difference between a world of hidden instructions and a world of genuine quantum indecision is loudest. The humble lens and the laboratory that cost millions are asking the very same question with the very same physics, only at different scales of care. Now feel the unease underneath the delight, because it is the same unease Einstein felt. If measuring a photon changes it, then what was true about the photon before you measured it? Was there any definite answer at all? Or did your filter conjure one into being? The three-filter trick does not by itself prove Bohr right. Einstein could still insist that hidden variables were being scrambled by the filters in some ordinary way, but it shows you, with light you can watch with your own eyes, that the quantum world does not behave like a drawer full of settled facts waiting to be read. It behaves like something that responds to the question you ask and answers differently depending on how you ask it. And this is exactly the property a Bell test needs. Remember what Bell required. He needed to measure two entangled particles at different, mismatched angles, and to see how their agreement behaved as those angles changed. Polarization gives you a perfect knob to turn. You can set Alice's filter at one angle and Bob's at another, and sweep them through every mismatched combination and count how often the two photons agree. The strange responsiveness of polarization, the way measurement remakes the thing measured, is precisely what makes the difference between the two worldviews finally show up in the numbers. So the pieces are gathering. We have Bell's theorem, which says a locally real universe must stay under a certain ceiling of agreement while quantum mechanics rises above it. We have entangled photons, born in matched pairs with linked polarizations. And we have polarizers, filters we can set to any angle to interrogate those photons and count the agreements. On paper, the experiment is now fully imaginable. You send entangled photons to two distant filters. You set the filters to a clever spread of angles. You tally how often the two sides agree, and you check which side of Bell's line the total lands on paper. In practice, in the real world of the 1960s and 70s, This was an enormous technical challenge. Entangled photons are hard to make in reliable pairs. Detectors are inefficient and miss most of what arrives. The angles have to be controlled with great precision, and the counting has to go on long enough to beat down the random noise. For years, the experiment existed only as a possibility, a thing that could be done in principle by someone with the patience and the skill and the stubbornness to actually build it. What that person needed, more than anything, was a willingness to spend years of his life chasing a number that most of his colleagues thought was a foregone conclusion, or worse, not worth measuring at all. And when he finally got his number, it was not going to be the one he was hoping for. Part 7. Alice, Bob, and a number called S. To turn Bell's beautiful theorem into something a real, imperfect laboratory could test, 4 physicists wrote a second paper in 1969. Their names were John Clauser, Michael Horn, Abner Shimony, and Richard Holt, and the reformulation they produced is known forever after by their 4 initials as the CHSH inequality. If Bell built the doorway, CHSH built the actual, usable handle you could grip to open it. What they did was take Bell's idealized argument and recast it as a single number you could assemble from real measurements, a number physicists usually call S. Do not let the letter intimidate you. S is just a scorecard. It is a way of combining how often 2 distant observers agree, across a few carefully chosen angle settings, into one figure that tells you which universe you are living in. Let me give you the setup, because it is the beating engine of every experiment that follows, and it has a friendly shape. We have 2 observers, and by tradition we call them Alice and Bob. A source in the middle sends out entangled photons in matched pairs, one flying to Alice, one flying to Bob. Alice has a polarizer she can set to one of 2 angles. Bob has a polarizer he can set to one of 2 angles. For each pair of photons, each of them chooses, at random, which of their 2 angles to use, and then records whether their photon got through or not. They do this thousands upon thousands of times, and afterward they compare their records and count, for each combination of angles, how often they agreed. Here is the fork in the road, and it is worth stating with total clarity because everything rides on it. Think about how the rate of agreement should change as Alice and Bob's angles drift apart. If their filters are lined up the same way, they should agree almost every time. If their filters are set opposite, they should disagree almost every time. The question is what happens at the angles in between, and this is exactly where the 2 worldviews part company. If the universe is locally real, if each photon carries hidden instructions written at the source that tell it what to do at any filter angle, then the rate of agreement has to change in a simple, restrained way as you rotate the filters, sliding along in proportion to the angle, in a straight and orderly line from full agreement to full disagreement. And when you combine the results across the 4 angle settings into that scorecard called S, a locally real universe can never, under any arrangement of hidden variables, push S above the value of 2. 2 is the wall. 2 is Bell's ceiling, written in the CHSH language. A local, real world lives at 2 or below, always, no exceptions. If instead quantum mechanics is right, the rate of agreement does not slide along a straight line. It follows a gentle curve, a cosine, that bulges outward above the straight line at the in-between angles. Entangled photons, at those mismatched settings, agree more often than any set of hidden instructions could arrange. And when you build the scorecard S out of the quantum predictions, it climbs past 2 all the way up to a maximum of 2 times the square root of 2, which is about 2.828. That upper limit even has its own name, the Cyrelson bound, the most tightly coordinated that quantum particles are allowed to be. Let me try to give you a feel for why the in-between angles are where the two worldviews betray themselves, because it is the subtlest and most beautiful part of the whole argument. Imagine you set Alice's filter and Bob's filter just a small angle apart, a sliver of a turn. In a locally real world, where each photon carries a fixed instruction sheet written at the source, a small change in Bob's angle can only flip a small fraction of his outcomes, because his answers were already written and only the ones near the boundary are affected. The disagreement grows in proportion to the angle, steadily, like a ramp. Now do the same in the quantum world. The disagreement does not grow along a straight ramp. It grows along a curve that starts out almost flat and then bends. And for small angles, the quantum world produces even fewer disagreements than the locally real ramp allows. Stack several of these small angle comparisons together, the way the scorecard adds them up, and the quantum curve pulls ahead of anything the ramp can match. That gap between the straight ramp of hidden instructions and the gentle curve of entanglement is the whole signal. It is small, it is subtle, and it is completely decisive. There is something worth pausing on in the fact that the difference is small. Nobody is measuring a wild, obvious factor of 10 discrepancy. The locally real ceiling is 2. The quantum world reaches about 2.8, and the experiments land somewhere above 2 with careful, hard-won precision. The entire revolution in our understanding of reality rides on the difference between a number that stays at or below 2 and a number that creeps past it. It is a reminder that the most important truths are not always loud. Sometimes the universe confesses its strangest secret not in a shout, but in a small, stubborn excess of agreement between two distant clicks, an excess that no arrangement of hidden instructions could ever have produced, showing up patiently in the totals after thousands upon thousands of pairs. So look at the gap. A locally real universe can reach 2 and not a hair more. A quantum universe can reach 2.828. Between 2 and 2.828 lies the entire question of what kind of reality you inhabit. Every Bell experiment ever performed is, at its core, a machine for measuring where, in that gap, the real number falls. Land at 2 or below, and Einstein wins, and the world is made of things with definite properties minding their own local business. Climb above 2, and there is no possible local, real story, and the comfortable universe is gone. I find this genuinely thrilling, and I want you to feel why. For thousands of years, the deepest questions about the nature of reality belonged to philosophers, and philosophers, for all their brilliance, could only argue, they could not measure. They could not force the world to testify. And here, in a single quantity built from photon counts, the question of whether reality is definite before you look at it has been boiled down to whether one number is bigger or smaller than 2. The universe has been handed a witness stand and a simple yes or no. It is almost unbearably elegant. The whole weight of the Einstein-Bohr war, 30 years of the greatest minds talking past each other, comes to rest on which side of 2 a photon-counting machine will land. There is one more thing built into this design that matters more than it might seem, and it will become the hero of a later part of our story. Notice that Alice and Bob choose their angles at random, independently, for each pair. This randomness is not decoration. It is essential. It is what stops the photons from cheating. If the filter angles were fixed and known in advance, you could always dream up some way for the particles to have arranged their answers ahead of time. By choosing the settings freshly and randomly, at the last possible instant, Alice and Bob make it as hard as possible for any local, real mechanism to keep up. Hold on to that idea of last instant random choice. Later, physicists are going to push it to a scale that borders on the absurd, choosing their angles using light that left distant stars before there were humans to build filters. For now, the machine is designed. The scorecard is defined. The wall stands at 2. The quantum ceiling stands at 2.828. All that remains is for someone to actually build the apparatus, generate the entangled photons, set the filters, and start counting. And the man who wrote the S into CHSH, John Clauser, was not content to leave his own scorecard sitting on paper. He wanted to measure it. He wanted the real number. So he set out to build with his own hands the first machine in history capable of asking the universe out loud whether it was locally real. And like Bell before him, he fully expected the universe to answer yes. Part 8. The first answer, and the man it disappointed. In 1972, at the University of California at Berkeley, John Clauser and a graduate student named Stuart Friedman finished building the first machine capable of measuring that scorecard, and switched it on. Their source of entangled photons was a beam of calcium atoms. When you excite a calcium atom in just the right way, it climbs to a high-energy state, and then, as it tumbles back down, it releases its extra energy in a quick two-step cascade, spitting out a pair of photons almost at once. Because of the way the atom is built and the rules the emission must obey, those two photons come out entangled in their polarization, linked together, a matched pair of exactly the kind Bell's theorem needs. On either side of the calcium beam, Friedman and Clauser placed a polarizer and a detector set at their carefully chosen angles, and then they began the long, patient work of counting coincidences, photon pair after photon pair, hour after hour. I want to put you in that room because it is one of the quiet hinge points in the history of human understanding, and it did not look like one. Picture the basement laboratory. It is not glamorous. There is the low hum of the equipment, the smell of warm electronics, a tangle of cables, the calcium source glowing faintly at the center of the apparatus. Two detectors sit at their stations on either side, clicking softly whenever a photon lands. A counter ticks upward. Friedman and Clauser move between the instruments, adjusting an angle, checking a reading, and then they wait, because the only way to get the number is to gather enough clicks to be sure the pattern is real and not just noise. Days pass this way. The counts accumulate. Somewhere on a sheet of paper, the scorecard is slowly filling in, point by point, and a curve is taking shape. And as the points land, they are not tracing the straight, restrained line that a locally real universe is allowed. They are tracing the outward bulge of the cosine, the quantum curve, the one that rises above the wall. Click by click, over days, in a Berkeley basement, the comfortable universe is quietly dying, and almost no one in the world knows it is happening. When the counting was done and the number was in, the scorecard had climbed clearly above 2. The Bell inequality was violated. The measurement missed the locally real prediction and matched the quantum one, and it did so by about 6 standard deviations, which, in the language of experimental physics, means the result was solid, not a fluke, not noise, but a real feature of the world. The very first time a human being had ever put the question directly to the universe had answered against Einstein. Reality, it said, is not locally real. Now here is the part that gives this moment its ache, and it is why I asked you to remember who was hoping for what. John Clauser did not want this answer. He had built the machine, by his own later account, expecting and hoping to prove Einstein right. He found quantum mechanics unsettling, and he thought, or at least he hoped, that his experiment would expose it as incomplete and reveal the sensible local reality he believed was hiding underneath. He spent years of his life constructing the apparatus that would vindicate the comfortable world. And then his own machine turned around and told him the comfortable world does not exist. Clauser said afterward, more than once, that he was disappointed by his own result. He had gone looking for Einstein's hidden variables, and instead he had helped bury them. Sit with that for a moment, because it is the mark of a real scientist and a rare kind of honesty. Quasar measured the thing he did not want to be true, saw that it was true, and published it anyway. He let the universe overrule his own deepest hope, and he told the world the answer, even though it was not the answer he had wanted to give. There is a quiet heroism in that, the willingness to be corrected by reality itself, to want one thing and report another, because the other is what the measurement said. There is a story from around this time that physicists have told for decades, and I have to be honest that I am not certain it happened exactly as told. Quasar himself recounted versions of it. As the story goes, excited despite his disappointment by the sheer significance of the result, Quasar went to tell Richard Feynman, one of the towering physicists of the age, what he had found, and Feynman, in the abrupt and theatrical way that was entirely his own, is said to have thrown Quasar out of his office, appalled that anyone had ever doubted quantum mechanics in the first place, and told him to go do some real physics. Whether or not the scene played out word for word like that, it captures something true about the mood of the era. The establishment did not think the question needed answering. To many working physicists, testing whether quantum mechanics was correct seemed almost like a waste of a good career, because of course it was correct, it always worked. Quasar had spent years measuring something the establishment considered already settled, and had gotten thrown out of an office for his trouble, and had, in the process, performed one of the most important experiments of the century. It is hard, from where we stand now, to appreciate how much of a gamble this was for a young physicist. Working on the foundations of quantum mechanics in the 1960s and 70s was widely seen as a way to damage your career, a soft and slightly embarrassing pursuit for someone who should be doing hard, respectable particle physics. The questions were considered either meaningless or already answered. Quasar has said he was warned it could be professional suicide, and for years the work brought him little reward and less recognition. He built a machine to test something almost everyone thought did not need testing, got an answer almost everyone had assumed in advance, and then had to wait decades for the world to understand that measuring the thing, actually forcing the universe to commit in a laboratory, was worth more than any assumption. The Nobel came 50 years after the experiment. Some truths take a long time to be believed, even after they have been proven. But even a 6 standard deviation result did not end the argument, and this is where the story gets even better, because a determined skeptic could still object. In the Friedman and Quasar experiment, the polarizer angles were set and left in place while the photons flew, and that left a gap, a loophole, that a clever defender of local realism could crawl through. What if, the skeptic could say, each photon somehow knew in advance how the distant polarizer was set? What if information about Alice's filter setting could leak over to Bob's side, travelling at or below the speed of light, in time to influence the outcome? The filters were not far apart, and they were not changing. There was time, in principle, for some slow signal to coordinate the two ends and fake the quantum result without anything truly spooky going on. The correlation might still have a local explanation if the two sides were quietly in touch. It was a real objection, and answering it would require something much harder. To close that loophole, you would have to change the polarizer settings so fast and so late, while the photons were already in flight, that no signal travelling at the speed of light could possibly carry the news from one side to the other in time. You would have to make the two measurements truly sealed off from each other, space-like separated, in the exact sense we talked about at the beginning. In 1972, the technology to do that did not quite exist. But there was a young physicist in France who was about to make it his mission, and who would take the entire question one enormous step closer to airtight. His name was Alain Aspect, and he was going to slam the first great door shut. Part 9. Slamming every door. In the early 1980s, at the Institute of Optics in Orsay, near Paris, Alain Aspect and his colleagues set out to close the loophole that Friedman and Quasar had left open. Their idea was as bold as it was simple to state and fiendishly hard to build. They would change the polarizer settings while the photons were already in flight. Think about why that matters. If the filter angles are fixed, a skeptic can always imagine some slow signal creeping from one side to the other, coordinating the outcomes. But if you wait until the photons have already left the source, already committed to their journey, and only then, at the last possible instant, flip the filters to new angles, chosen too late for any light speed message to cross the gap, then there is simply no time for the two sides to conspire. The measurement on Alice's side and the measurement on Bob's side become sealed off from each other, space-like separated, in the strict sense that not even light could carry the news between them in time. Whatever correlation survives, that cannot be explained by any signal passing between the ends, because no signal could have made the trip. Aspect's team built switches that could redirect the photons between different polarizer orientations every 10 nanoseconds or so. 10 nanoseconds is 10 billionths of a second, a slice of time so thin that light itself travels only a few meters within it, less than the distance between the two stations. The switching was fast enough, and the stations far enough apart, that the choice of setting on one side could not possibly reach the other side before the measurement was done. In their 1982 experiment using these rapidly changing analyzers, Aspect and his colleagues ran the whole scheme and read off the scorecard. It landed above 2 again, near 2.4, comfortably violating Bell's wall and matching the quantum prediction. The correlation held even when the two sides had no way to communicate. One great door, the communication loophole, swung shut. I want to slow down and ride along with those photons for a moment, because there is a strange calm buried inside this frantic engineering. Follow a single entangled photon as it leaves the source and begins its short flight toward one of the stations. It is moving at the one speed the universe truly honors, the speed of light, the fastest anything can go. For 10 billionths of a second, it simply travels, serene, through the apparatus, carrying whatever it carries. Ahead of it, the filter it will meet has not yet chosen its angle. Behind it, the source is already sending the next pair. And its distant partner, flying the opposite way, is having the same quiet journey in reverse. Neither photon can send the other any message. Neither knows what filter angle waits at the end. They are two travelers moving apart at the pace of light, utterly out of contact, and yet when they finally arrive and are measured, their answers will match more tightly than any pair of messages ever could have arranged. There is something almost peaceful in it. The universe forbids them to speak, and they agree anyway. Then came Anton Zeilinger, the third of our laureates, whose groups in Innsbruck and later Vienna pushed the whole program to its limit and passed it. In 1998, a young physicist named Gregor Ways, working with Zeilinger, ran a Bell test with the two stations separated by 400 meters, more than a quarter of a mile, and with the filter settings chosen by fast, physical, random number generators making genuinely unpredictable choices at each end. This was the cleanest realization yet of exactly the space-like separation Bell's argument called for. The two measurements sealed off from each other in both space and time, the choices as free and last instant as the technology could make them, and the scorecard climbed over 2 once more. The universe picked the same side it had picked in Berkeley, the same side it had picked in Orsay. Zeilinger's group did more than close loopholes. In 1997, they demonstrated something that sounds like it belongs in fiction, called quantum teleportation, in which the complete quantum state of one photon is transferred onto another distant photon, using entanglement as the channel. They built entangled states of 3 particles at once. They performed a trick called entanglement swapping, entangling 2 particles that had never so much as met. They sent entangled photons between 2 of the Canary Islands, across 144 kilometers of open air. Everywhere they looked, At every distance, the correlations held, always above the wall, always on the same side. The capstone came in 2015. By then, a second loophole still nagged at the most careful skeptics, called the detection loophole. Real detectors miss most of the photons that reach them, and a determined defender of local realism could argue that the ones we happen to catch might be a biased, unrepresentative sample, secretly hiding a locally real explanation in the ones we miss. Closing this required detectors efficient enough to catch a large fraction of the pairs over enough distance, with fast enough switching to shut both the communication loophole and the detection loophole at the same time in a single experiment. In 2015, 3 independent groups did exactly that, one in Delft in the Netherlands, one in Vienna, and one at the National Institute of Standards and Technology in the United States. For the first time, every major loophole was closed together. The result held. The scorecard climbed over 2 with no remaining escape route. Local realism was no longer merely disfavored, it was finished. I want to make sure you appreciate the pattern in all of this, because it is a model of how careful science actually works. Each experiment did not simply repeat the last one. Each one identified a specific, nameable way that a determined skeptic could still cling to local realism, and then closed exactly that escape. Friedman and Quasar showed the correlation was there. Aspect showed it survived when the two sides could not communicate. Wise and Zeilinger showed it survived with genuinely free, last instant, random choices and clean separation. The 2015 experiments showed it survived even when you insisted on catching enough of the particles to rule out a biased sample. Every objection got its own dedicated experiment, built specifically to answer it, and every single time the answer came back the same. This is not one result that might be a fluke. It is a converging wall of independent results, each sealing a different crack, all pointing at the identical conclusion from different directions. That convergence is why physicists speak about this with a confidence they reserve for very few things in all of science. And then physicists did something that sounds like paranoia and is actually the purest rigor. There remained one last, almost philosophical loophole called the freedom of choice loophole. What if the random choices Alice and Bob make about their filter angles are not truly free? What if those choices are somehow correlated through some chain of causes with the hidden properties of the particles themselves? To attack this, experimenters decided to hand the choice of filter setting not to a machine in the lab, but to the universe at large. They used the color of light arriving from distant stars, and then, more astonishingly, from quasars, billions of light years away, to decide, at the last instant, how to set each polarizer. Let me put you at that telescope, because it is one of the most beautiful things human beings have ever arranged. A single photon of light left a quasar, a blazing beacon at the core of a distant galaxy, billions of years ago, when the Earth did not yet exist. For all that time, it has been crossing the emptiness between galaxies, alone, untouched, moving at the one-honored speed, carrying nothing but its color and its long history. Tonight, at last, it arrives at a telescope on a mountain. Its color is read in a fraction of a second, and that color, decided billions of years ago and light years away, is used to flip a polarizer to one angle or the other, a nanosecond before an entangled photon down in the laboratory arrives to be measured. The universe itself, reaching across almost the whole age of creation, has chosen the setting, and if some local, real conspiracy were secretly fixing the outcomes, it would have had to have been set in motion billions of years ago in opposite corners of the sky, aimed with impossible precision at a handful of physicists on a particular mountain on a particular night. The correlation held here too. The scorecard climbed over 2 even when the quasars called the shots. So here we are. I told you a long while ago that after Bell, the universe would have to pick a side. Now you have watched it choose, over and over, across 50 years, in Berkeley and Orsay and Vienna and Delft, with switches and random generators and the ancient light of quasars, with every loophole walked to and locked in turn. And every single time, without one exception, the universe picked the same side. It is not locally real. The question is no longer whether that is true. The question that remains is far stranger, and we have to face it now. If the world is not locally real, then which of our two precious assumptions do we actually have to give up? Part 10. So, which one do we lose? Here is the subtle thing that most headlines about this discovery get wrong, and I want to be very careful and very honest with you about it, because it is where the real depth lives. The experiments do not tell you that the universe is non-local, and they do not tell you that the universe is not real. What they tell you is that the universe cannot be both at once. Locality and realism together are ruled out. But which one you surrender is not settled by the data. The measurement forces a choice on you, and then it steps back and lets you choose. This is why, more than 90 years after the argument began, physicists still disagree about what quantum mechanics means, even though they agree completely about what it predicts. The disagreement is no longer about the numbers. Everyone gets the same numbers. The disagreement is about which comfortable assumption to give up in order to explain those numbers, and each answer is its own interpretation of quantum mechanics, its own picture of what is really out there. The most common answer, the one woven into the standard textbook view descended from Bohr and Copenhagen, is to give up realism. On this reading, the particles genuinely do not have definite properties until they are measured. The photon has no settled polarization until it meets a filter. The property is not hidden from us. It is simply not there yet, and measurement is the act that brings it into being. This is the view the three-filter sunglasses trick was quietly pointing at all along. If you are willing to accept that the small world has no definite facts until it is interrogated, then you can keep locality, keep the speed limit sacred, and pay for it by admitting that reality, at bottom, is not written down in advance. But there is another way to pay the bill, and it does the opposite. A theory called Bohmian mechanics, the pilot wave picture developed by Louis de Broglie and later David Bohm, chooses to keep realism and give up locality instead. In this picture, particles always do have definite positions, real and settled at every instant, exactly as Einstein wanted. But they are guided by a wave that is openly, unashamedly non-local, a wave that stretches across all of space and responds instantly to what happens anywhere in it. Change Alice's filter, and the guiding wave over on Bob's side shifts in the same instant. Bohmian mechanics reproduces every single quantum prediction, matches every experiment, violates Bell's wall exactly as observed. It simply pays for keeping definite reality by accepting the faster-than-light connection that Einstein could not stomach. It is the mirror image of Copenhagen. Same numbers, opposite sacrifice. And then there is the strangest option of all, the one that keeps both locality and definiteness by giving up something you might not have thought was on the table. It is called the many worlds interpretation, and it proposes that every possible outcome of every measurement actually happens, each in its own branch of a constantly dividing reality. Let me try to place you inside that idea for a moment, gently, because it is the most vertiginous of them all. Imagine Alice, about to measure her photon. In the ordinary telling, the photon settles on one answer and the other possibility simply vanishes. But in the many worlds picture, nothing vanishes. Instead, at the instant of measurement, the world quietly divides. It does not tear or flash or make any sound. Picture a calm river arriving at a smooth stone and parting around it, slipping into two channels, each one carrying the current onward without a ripple of struggle. In one channel, Alice sees her photon pass, and there is a version of her who now knows that result. In the other, Alice sees it blocked, and there is a version of her carried down that branch instead. Neither Alice feels anything split, neither is aware of the other. Each simply finds herself in a world with one definite outcome, and the strange coordination with Bob's distant result is explained not by any signal, but by the way the branches on both sides line up as the division spreads outward at the ordinary pace of light. No faster-than-light influence, no collapse. Just an endlessly branching reality in which every version of every measurement is realized somewhere, and you only ever notice the branch you happen to ride. I am not going to tell you which of these is correct, because nobody knows, and anyone who tells you they are certain is selling you their taste as if it were a fact. Copenhagen gives up definite reality. Bohm gives up locality. Many worlds gives up the single outcome. There are others still, quieter ones, that locate a particle's properties in the relationship between the thing and its observer rather than in the thing alone. Each of these is held by serious, brilliant physicists. Each one fits all the data perfectly, because the data only forbids the one comfortable combination, locality and realism together, and says nothing about how you cope with the loss. Now let me return to the two gloves in their two boxes, because I promised you they would come back wearing a different face, and this is the moment. Remember Einstein's picture. A left glove in Lima, a right glove in Tokyo, decided at the moment of packing, merely revealed at the moment of opening. It was the most persuasive image in this whole story, and for ordinary gloves it is exactly right. But the Bell experiments have shown us that entangled particles are not like the gloves. If they were, the scorecard would sit at 2 or below forever. It does not. It climbs above 2. And that means the analogy breaks in the most unsettling way imaginable. It is as if the gloves did not decide their handedness when they were packed. It is as if each glove waited, undecided, in its sealed box, and only at the instant someone in Lima opened one did the pair, across all those thousands of miles, somehow settle together which was left and which was right, and settle it more perfectly than any prior arrangement could have. The gloves that so comforted us have become the very thing we cannot explain. The suitcase, it turns out, was not packed before the journey after all. That is the vertigo, and I want you to let it be gentle rather than frightening, because there is nothing here that will hurt you. The floor of your intuition has tilted. That is all. The world you live in is not made of little objects carrying settled properties and minding their local business. It is made of something that refuses that description, something that can be definite or local but not both, something that answers the question you ask in a way that depends on the asking. You do not have to resolve which interpretation is true tonight. Nobody has. You only have to sit with the fact that the cozy picture, the one your mind hands you for free, is the one option the universe has definitively ruled out. But maybe, even now, a hopeful thought is forming. If measuring a particle here instantly does something to its partner there, across any distance, then surely we can use this. Surely we can send a message with it, a signal faster than light, a way to beat Einstein's speed limit at last. It is the most natural idea in the world, and almost everyone has it the first time they truly understand entanglement. I had it. You may be having it right now. And it is exactly here that the universe reveals its final, most elegant piece of craftsmanship. Because the answer, strange and beautiful and firm, is no. And the reason why is one of the most perfect things in all of physics. Part 11. The message you can never send. The reason you cannot send a message with entanglement comes down to a single word, and the word is randomness. Let us go back to Alice and Bob one more time and think very carefully about what each of them actually experiences. Alice measures her photon and gets a result. But here is the crucial thing. She cannot control that result, and she cannot predict it. When she measures, the outcome she gets is genuinely random. It is not that she is choosing to send Bob a 1 or a 0. The universe is flipping the coin, not Alice. She simply receives whatever comes, an unpredictable string of yeses and nos, and there is nothing she can do to bias it, steer it, or load a message onto it. Now think about what Bob sees on his side, all by himself, before he ever talks to Alice. He too gets a string of results, and looked at on their own, his results are just as random as hers. If you handed Bob his data and told him nothing else, he would see nothing but noise, a meaningless scatter of outcomes with no pattern in it at all. Nothing in Bob's data, by itself, changes depending on what Alice did. He cannot look at his own photons and tell whether Alice has measured hers, or how she set her filter, or whether she has done anything at all. His side of the experiment looks exactly the same either way. This is the quiet, decisive fact that saves Einstein's speed limit. Neither party, looking only at what they hold, can detect anything the other did. So where is the famous correlation? Where is the spooky link everyone talks about? It is real, but it only appears when you lay the two lists of results side by side and compare them, entry by entry. Only when Alice's random string and Bob's random string are brought together and matched up pair by pair does the eerie coordination reveal itself, the agreement stronger than any locally real world allows. Apart, each list is noise. Together, they sing. But to bring them together, someone has to physically carry one list to the other, and that carrying, that comparing, happens over an ordinary channel, a phone call, an email, a signal, something that itself cannot travel faster than light. The correlation is invisible until the two halves are reunited, and reuniting them is bound by the very speed limit you were hoping to break. This is why the field is nearly unanimous, and it is not a matter of opinion or caution, it is a theorem with a name. It is called the no communication theorem, and it proves, rigorously, that no measurement one party makes on their half of an entangled pair can transmit any information to the other party. The non-local correlation is real. The non-local signal does not exist. The universe threads a needle so fine that almost no one would have guessed it was there. It allows the correlations to be stronger than locality should permit, and in the same breath it forbids those correlations from ever carrying a usable message. It is spooky and lawful at the very same time. I find this one of the most quietly astonishing things in all of physics, and I want you to feel the relief and the wonder braided together in it. Einstein was wrong about local realism. The world is not made of definite things minding their local business. And yet, the single principle he cared about most, the one that sits at the very foundation of his relativity, the principle that nothing, no influence, no signal, no scrap of information, can outrun light, that principle survives completely intact. The universe reached into Einstein's worldview, took away the comfortable picture of definite local reality, and left the speed limit standing without a scratch. It is as if the cosmos went out of its way to be strange in every way except the one way that would have broken causality itself. Think about what a catastrophe it would be if it were otherwise. If you could send signals faster than light, you could, according to relativity, send signals backward in time. You could arrange for messages to arrive before they were sent, for effects to precede their causes, for the whole orderly structure of before and after to dissolve into paradox. The speed limit is not a mere traffic rule. It is the thing that keeps cause ahead of effect, that keeps the universe from tangling itself into contradictions. And the astonishing discovery at the center of tonight's story is that the universe found a way to be radically, provably non-local in its correlations, while never once letting those correlations threaten causality. It kept the one rule that truly mattered. So the dream of the faster-than-light telephone dies, and it dies for a beautiful reason. The entangled connection is real, but it is not a wire you can talk down. It is more like two coins, minted together, that always land as perfect opposites, no matter how far apart you flip them, and yet each individual flip is so utterly random that neither coin can be used to spell out a word. You can verify the impossible coordination only afterward, by comparing notes through ordinary means. The precise reason this works is worth turning over slowly, because it is the hinge on which causality survives. For a message to travel, the receiver has to be able to tell the difference between the sender doing one thing and the sender doing another. That is what information is, at bottom, a detectable difference. And the no communication theorem proves that Bob's side of the experiment looks statistically identical no matter what Alice does, no matter which filter angle she picks, no matter whether she measures at all. Every pattern Bob can compute from his own data alone is exactly the same in every case. There is no detectable difference on his end, and so there is no message, not because we are not clever enough to read it, but because there is genuinely nothing there to read until Alice's list arrives by ordinary means. The moment you try to use the connection to signal, the randomness swallows the signal whole. It is a kind of perfect censorship, built into the structure of the world, guarding the order of cause and effect from the very non-locality that same world allows. The magic is real, and the magic is useless for sending messages, and those two facts live together in perfect peace. This does not mean entanglement is good for nothing. Far from it. As we will see in a moment, it is the engine of a coming technological revolution. But it does mean that the one thing everybody first imagines, instant communication across the galaxy, is off the table, forbidden not by our lack of cleverness, but by the fundamental structure of the theory itself. Einstein lost the argument about reality and won the argument about speed, and somehow both of those are true at once, and the universe holds them together without the slightest strain. There is one more thing we have to face before we can rest, though one loose thread I have been quietly leaving untied this whole time. I have told you, again and again, that every loophole has been closed, that the universe has picked the same side every time, that local realism is finished. And that is true, with a single, subtle, almost unbelievable exception. There remains exactly one way to save the comfortable universe, one escape hatch that no experiment can ever fully bolt shut, not even in principle. Almost every physicist refuses to walk through it. A few brilliant ones insist we must. And to understand what it is, and why it is both a real possibility and a terrible price to pay, we have to look at the strangest idea in this entire strange story. Part 12. The One Escape Hatch and Its Price. The escape hatch is called superdeterminism, and to see how it works, you have to go back and look at a hidden assumption buried inside every Bell test, one so natural that we barely noticed we were making it. Every one of these experiments assumes that Alice and Bob freely choose their filter settings, independently of whatever hidden properties the particles happen to carry. When Alice's random generator picks an angle, we assume that choice has nothing to do with the secret state of the photon flying toward her. That independence is the quiet foundation the whole proof stands on. It is what lets us say that if the correlations are too strong, no local, real story can explain them. Superdeterminism denies exactly that assumption. It proposes that the settings and the particle properties were never independent at all. It says they were correlated from the very beginning, both of them determined together by the same web of causes reaching all the way back to the birth of the universe. Think about what that would mean. If the choice Alice's generator makes and the hidden state of the photon it measures were both fixed in advance by a common chain of causes stretching back billions of years, then the apparent violation of Bell's wall would be an illusion. The particles would not need to communicate faster than light, and they would not need to lack definite properties. They would simply have been set up at the dawn of time, so that the choices and the outcomes would always dovetail into a pattern that looks like quantum weirdness, but is really just a cosmic script playing out exactly as it was written. Local realism survives, but only by surrendering the idea that the experimenters were ever free to choose anything at all. This is not the raving of cranks. Some genuinely great physicists take it seriously. The Nobel laureate Gerard Hooft has argued for versions of it. The physicist Tim Palmer has developed careful models along these lines. They are not fools, and superdeterminism is not logically impossible. In fact, it cannot be ruled out by any experiment, and that is the maddening part, the reason it deserves its place as the last escape hatch. To fully close it, you would need a choice that was truly, absolutely uncaused by anything in the particle's past, and no measurement can ever guarantee such a thing, because you can never prove that two events share no common cause somewhere back along the infinite chain of history. But look at what the physicists did to this idea. They did not ignore it. They attacked it with the most beautiful experiment in the whole saga, the one where the filter settings are chosen by the light of quasars billions of light years apart. Remember what that accomplishes now, in this new light. If superdeterminism is true, and the choices and the outcomes were coordinated in advance, then the coordination would have to have been arranged not in the laboratory, not a moment before the measurement, but billions of years ago, in two opposite corners of the visible universe, in the cores of two quasars that have never had any contact with each other, and aimed with flawless precision at one particular experiment, on one particular night, on one particular planet. The physicists could not disprove superdeterminism because it cannot be disproven, but they raised its price to something almost no one is willing to pay. Let me ask you to sit inside that price for a moment, because it is one of the most uncanny thoughts a human being can hold. To keep the comfortable, locally real universe, you must believe that the cosmos arranged itself, at the very beginning, across its entire span, so that a handful of scientists in a basement would be steered by the ancient light of distant quasars to set their dials in precisely the way that would fake the death of local realism. You must believe the universe planned this. Every experiment, every choice, every quasar photon, all of it choreographed from the first instant so that reality could wear a disguise. That is what it costs to save the world your intuition wants. Most physicists take one look at that price and quietly decline to pay it. A few pay it gladly and hold the line for local realism, kept alive not by any evidence in its favour, but by the sheer impossibility of ever ruling it out. I want to be fair to both stances, because this is where honest people genuinely diverge. The mainstream view is that superdeterminism, while logically airtight, asks you to believe in a conspiracy so total and so finely tuned that it explains everything and predicts nothing, and that a theory which can never be tested and which demands a universe-spanning setup arranged at the Big Bang has left the domain of science for something closer to fatalism. The defenders answer that giving up the free independence of measurement choices may be less radical than giving up locality or definite reality, and that our attachment to experimental free will is itself just an assumption. I will not tell you who is right. I will only tell you that this is the one surviving refuge of the locally real universe, and that it survives not because we found it, but because we can never chase it all the way down. While we are naming tempting escape routes, let me clear away one that is not real, because you will hear it constantly, and it is a misunderstanding. Some people, hearing that measurement collapses the wave function, and that measurement seems to require an observer, leap to the conclusion that human consciousness must be what creates reality, that the mind is the magic ingredient that makes the world definite. It is a seductive idea, and it is not what the physics says. In quantum mechanics, an observer is not a conscious being. A measurement is any interaction that irreversibly entangles a particle with a larger system, and that happens constantly, everywhere, with no mind anywhere near it. A stray air molecule measures a particle. A photon of sunlight measures it. A cold rock far out in the dark measures it. The universe was collapsing wave functions for billions of years before there was a single eye to see. The measurement problem is real and unsolved, but it is not a doorway to mysticism, and it does not put your mind at the center of the cosmos. Set that idea gently aside. The strangeness is real. It just is not about you watching, so the accounting is nearly complete. The universe is not locally real. It cannot send you a message faster than light. And the single way to rescue the old, comfortable picture requires believing in a cosmic conspiracy so enormous that almost no one can stomach it. I told you at the start that after Bell, the universe would have to pick a side, and now you understand the full truth of that sentence. It has picked, over and over, for 50 years. The only way to unpick its choice is to believe the choice was rigged from the beginning of time. That is where we stand. And it would be easy to leave it there, as a strange and slightly cold fact about distant particles in distant laboratories. But that would be a mistake, because this is not a fact about laboratories. It is a fact about the chair you are sitting in, the floor beneath it, and the body reading these words. We have one thing left to understand, and it is the most personal of all. Part 13. The strangeness you are made of. The last thing you need to know is that the strangeness we have been circling all night is not locked away in distant laboratories. It is the ground you are standing on, and it is also, quietly, the future. Let me start with the future, because it is the happier turn. Remember the final words of that Nobel citation, the phrase I read you at the very beginning. Aspect, Clauser, and Zeilinger were honored not only for establishing the violation of Bell inequalities, but for pioneering quantum information science. That last phrase points forward, and it turns the whole story around in the most satisfying way. The very entanglement that Einstein tried to banish as too spooky to be real has become a resource, a raw material, the fuel of a coming technological revolution. The same correlations that break local realism are the thing that quantum computers run on. A quantum computer draws its power from particles that are entangled in exactly this Bell-violating way, communicating their linked states so that the machine can, in principle, explore many possibilities at once and outrun any ordinary computer on certain problems. The strangeness is not a curiosity, it is an engine. Entanglement is also quietly making the world's secrets safer. There is a way of sharing secret keys called quantum cryptography that uses a Bell test itself as a guarantee. Because any eavesdropper who tried to intercept the entangled particles would disturb the correlations and break the Bell violation, two distant parties can check the scorecard and know, with the certainty of physics, whether anyone has been listening. The death of local realism, the very thing that so disturbed Einstein and Clauser and Bell, has been turned into a tool for building unbreakable locks. The thing they did not want to be true became a thing we can use. It is worth letting the strangeness of that sink in gently, because it closes a circle that took a century to draw. When Einstein and his colleagues wrote down entanglement in 1935, they offered it as a reason to distrust quantum mechanics, a symptom of everything wrong with the theory, a spookiness so absurd it surely signaled a mistake. They meant it as the theory's greatest embarrassment. And now, 90 years later, that same embarrassment is the most valuable resource in one of the most promising technologies our species has ever pursued. Engineers spend their careers learning to create entanglement, protect it, and put it to work. The thing Einstein pointed to and said, "This cannot be right," is the thing we now build elaborate machines to preserve. History rarely turns a thinker's sharpest objection into his successor's most prized tool, but that is exactly what happened here, and there is a strange justice in it. But set the technology aside now, because we are near the end, and I want to bring this all the way home, to you, in the room where you are listening. Everything around you is made of particles that behave the way we have described. The chair beneath you, the wall you are facing, the blanket over you, the very cells of the hand at the end of your arm, all of it is built, at the smallest level, out of the same kind of quantum stuff that refuses to be both local and real. The solidity you feel, the definiteness of the objects in your room, the reassuring there-ness of the world, all of that is real in the way that matters to your life. But it is a large-scale average, a statistical calm that emerges when countless quantum pieces are added together. Underneath that calm sits a substrate that, measured directly, one particle at a time, will not commit to the comfortable picture. You are not standing on top of the strangeness, watching it from a safe distance. You are made of it. You always have been. Let me give you the room to feel this, softly, as a place to rest, rather than a place to worry. Look, in your mind, at the space around you in the dark. The furniture you know is there, the walls holding the quiet, the air, the floor, the weight of your own body settling into the bed or the chair. Now, let all of it loosen, just a little, in your imagination. Let the solid shapes soften into what they actually are, unimaginable numbers of tiny particles, each one part of that same quantum fabric, each one refusing, at its core, to be a small, definite thing, minding its own local business. The room does not become less safe for this. It becomes stranger and gentler at once, a still surface resting on a depth that does not obey the rules you were taught. You are lying in a lattice of the very thing 3 physicists won the Nobel Prize for understanding. The definite world is a truce drawn across a reality that never signed it, and you are held, right now, inside that truce, perfectly safe, on top of something wonderfully strange. I gave you a sentence early tonight, and I asked you to remember it, and to notice that there was a moment when it still sounded like nonsense. The sentence was, "None of it is real until you look." When Bohr's camp first said something like it, almost a century ago, it sounded like a provocation, like a riddle you could dismiss. Say it to yourself now, here at the end, and feel how much heavier it has become. It is no longer a slogan. It is close to a measured fact, tested in Berkeley and Orsay and Vienna and Delft, checked against the ancient light of quasars, confirmed every single time. None of it is real, in the old, comfortable sense of definite properties waiting to be found, until it is measured. That is not philosophy anymore. That is what the experiments say. And here is the thing I most want you to carry with you as you drift off. This is not a sad discovery, and it is not a frightening one. It is one of the most extraordinary things our species has ever done. A few human beings, armed with calcium atoms and polarizing filters and a great deal of patience, asked the universe a question that had seemed forever beyond asking, a question about the deepest nature of what is real, and the universe answered. It did not stay silent. It picked a side, and it told us, in a number, that reality is stranger and subtler than the picture we are born believing. Einstein, who was wrong about this, was wrong in the most productive way anyone has ever been wrong, because the sharpness of his objection is the very thing that made the answer findable. He handed his opponents the blade that would settle the argument against him, and there is a kind of greatness in that too. Think back to that ordinary autumn morning in Stockholm, the 4th of October, 2022, where we began. A committee read out a sentence that said, in effect, the world is not locally real, and then the day went on as days do. Most people never heard. The sun came up. And yet, sitting inside that quiet announcement was the end of a 100-year argument and the confirmation of one of the most beautiful and unsettling facts a mind can hold. The universe you live in is not made of little certain things keeping to themselves. It is woven from something that holds its answers loosely, that responds to the questions we ask, that binds distant particles together more tightly than any signal could, and still, gracefully, forbids them to speak. That is the world. That is the real one. It was always the real one. We only just learnt how to hear it say so. So let the strangeness settle over you now, not as a puzzle to solve, but as a quiet companion for the night. The particles in the walls, in the air, in you, are all part of the same soft, uncertain fabric, and there is nothing to fear in that, and nothing you need to do about it. The great argument is over. The answer is in. Reality is not what we thought, and the world goes on being beautiful and holding you exactly the same. You can rest inside that. You can close your eyes on a universe that is far more interesting than the one you were promised, and let the not quite real, not quite local fabric of everything hold you gently while you sleep.